Blade, single-view body mesh estimation through accurate depth estimation. Recent advances in 3D human mesh recovery, or HMR, have started to democratize motion capture for media production, allowed computers to understand human gestures for human-computer interaction, and enabled new applications in healthcare, fitness, and virtual try-on for e-commerce. Despite the many successes, current methods struggle with up-close images and in scenarios such as video conferencing, thus creating problems when labeling large-scale and diverse image datasets captured in the wild. We present Blade, a novel method that accurately recovers the human mesh and perspective camera parameters from a single image. Single-image human mesh recovery is challenging due to the under-constrained nature of estimating many parameters from a monocular view. Intrinsic and extrinsic camera parameters are unknown for in-the-wild images and need to be estimated in addition to human shape and pose. It is exceptionally difficult to jointly estimate all variables at once. Scale ambiguity and the unknown shape of a person contribute to the existence of a potentially infinite number of valid yet incorrect solutions. Most existing methods reduce the number of unknowns by assuming near orthographic projection and estimate the camera focal length heuristically. To fulfill these assumptions, the person in the image has to be far away from the camera. This is not always true in practice and can lead to unsatisfactory results, especially for close-ups that show a person with strong perspective distortion. The state-of-the-art method, XALI, is a perspective-aware model which allows human mesh recovery from close-range images by estimating the pelvis distance TZ. However, XALI uses inaccurate approximations that can lead to an incorrect projection. Our method is different in the sense that it fully departs from relying on heuristics during perspective camera parameter estimation. Our key observation is that, mathematically, the amount of perspective distortion is inversely proportional to the distance between camera and person. The camera's focal length does not affect distortion, but merely acts as a zoom factor. Motivated by this intuition and the recent success of one-shot metrical depth estimators, we build a module for TZ estimation. Once TZ is estimated, the other variables become easier to solve, and the human mesh can be estimated more accurately. Given a single image, our goal is to estimate an accurate 3D mesh of the person as simple X parameters, while simultaneously achieving good 2D alignment. We introduce a 3-step human mesh recovery pipeline that solves for 1. The Z translation TZ of the person with respect to the camera, 2. The 3D human pose and shape as simple X parameters beta, theta, and 3. The person's XY translations TX, TY, and a camera focal length F. Our method works as follows. Starting with a cropped image around a person which is estimated from the input image, the pelvis depth estimator estimates the Z translation of the person's pelvis TZ with respect to the camera. Then, from the full image, the pose estimator derives simple X parameters, beta and theta, for shape and pose while being conditioned on TZ. Finally, through differentiable rasterization, the camera solver recovers the optimal focal length and 3D translation that best align the rendered simple X mesh with a segmented mask of the person. Using this pipeline, Blade solves for the human mesh and fully perspective projection model without heuristics in the estimation of camera parameters. Existing labeled datasets for human mesh recovery lack close-range images with strong perspective distortion. To augment them, we created a new large-scale synthetic dataset with 2 million images tailored to this task. We use assets from the Bedlam dataset and therefore call our dataset Bedlam Close Camera, or Bedlam CC for short. For our dataset, the distance between person and camera is sampled using an inverse TZ weighting to generate more close-up samples that are especially challenging for estimators due to the higher amount of perspective distortion. With a wider range of depths, the Bedlam CC dataset helps our model to accurately learn the Z translation and 3D pose of the human body. Here we show examples of the dataset. The variation in lighting and camera angles as well as strong perspective distortion, are intentionally part of the data. With publication of the paper, we will also release the code to render the dataset. Our method BLADE outperforms existing methods on several benchmark datasets captured at diverse depth ranges in terms of TZ error, focal length, 3D pose, and 2D alignment. Please check our paper and supplemental material for the detailed quantitative evaluation. BLADE can be used to accurately recover the human meshes and camera labels for large in-the-wild image datasets, including close-ups and images with strong perspective distortion. We presented BLADE, the first single-image human mesh recovery method to accurately estimate a fully perspective projection model without relying on heuristics or weak perspective assumptions. Thanks for watching.